Hi, Assalamualaikum and good day. Today you are going to learn on how to solve the maximum and minimum values problems. This is the objective of today's lesson. Hopefully, by the end of this session, you should be able to solve problems involving maximum and minimum values. Many practical problems require us to minimize a cost or maximize an area or somehow find the best possible outcome of a situation. Following are the procedures for solving maximum and minimum values problem. 1. Understand the problem. 2. Draw an appropriate figure and label the quantities. 3. Identify the suitable formula for the problems. 4. Find the x value when dy over dx is equal to 0. 5. Apply the second derivative test to determine whether y is maximum or minimum. And finally, insert x equal to c into y in order to obtain the maximum or minimum value of y. Refer to example 1. Find the dimension of a rectangular field with maximum area that can be enclosed with 1000 feet of fence. To solve the problem, first of all, identify all the unknowns involved. For this example, x refers to the width, y refers to the length, and a refers to the area of the rectangular field. The rectangular field can be represented by the following figure, given that the perimeter of the rectangular field is 1000 feet. The perimeter is represented as 2x plus 2y equal to 1000. Simplify this equation, you will get x plus y equal to 500. Thus, y is equal to 500 minus x. The area of the rectangular field is represented as A equal to xy. Replace y with 500 minus x and simplify the equation. You will obtain A equal to 500x minus x squared. Differentiate a with respect to x, you will get dA over dx equal to 500 minus 2x. By letting dA over dx equal to 0, you will obtain x equal to 250. Differentiate dA over dx once again with respect to x, you will get dA squared over d squared x equal to -2, which is less than 0. Therefore, the area is maximum at x equal to 250. When x is 250 feet, y is also 250 feet. Therefore, the dimension is equal to 250 feet by 250 feet. Now, refer to example 2. A closed cylindrical can of radius r and height h is to have volume of 128,000 cm3. Show that the surface area is represented as A equal to 2 pi r squared plus 256,000 over r. Then, find the radius that minimizes the surface area. For this example, r refers to the radius, h refers to the height, and A refers to the surface area of the closed cylindrical can. The cylindrical can can be represented by the following figure, given that the volume is 128,000 cm3. The volume is represented as pi r squared h equal to 128,000. Simplify, you will obtain h equal to 128,000 over pi r squared. The area of the closed cylinder is represented as A equal to pi r square plus pi r square plus 2 pi r h. Simplify this by substituting h with 128,000 over pi r square. You will obtain A equal to 2 pi r square plus 256,000 over r. Next, differentiate A with respect to r. You will get dA over dr equal to 4 pi r minus 256,000 over r square. By letting dA over dr equal to 0, calculate for the value of r. You will get r equal to 27.31 centimeter. Differentiate dA over dr once again with respect to r. You will get d square A over dr square equal to 4 pi plus 512,000 over r cubed. Substitute r with 27.31 and simplify. You will obtain d square A over dr square equal to 37.7, which is greater than 0. Thus, the area is minimum at r equal to 27.31 centimeter. In other words, the radius that minimizes the surface area is 27.31 centimeter. Refer to example 3. A closed rectangular container with a square base is to have a volume 2,250 cm3. The material for the top and bottom of the container will cost 2 ringgit per centimeter square, and the material for the sides will cost 3 ringgit per centimeter square. Find the minimum cost of the constructing the box. For this example, x refers to the size of the square base, h refers to the height of the container, and c refers to the cost of constructing the box. The container can be represented by the following figure, given that the volume is 2,250 cm3. The volume is represented as x square h equal to 2,250. Simplify, you will obtain h equal to 202,050 over x square. The cost of constructing the box is represented as C equal to 2x square multiplied with 2 plus 4hx multiplied with 3. Substitute h with 2,250 over x square and simplify. You will obtain C equal to 4x square plus 27,000 over x. Next, differentiate c with respect to x. You will get dc over dx equal to 8x minus 27,000 over x squared. By letting dc over dx equal to 0, calculate for the value of x. You will obtain x equal to 15 centimeter. Differentiate dc over dx once again with respect to x. You will get d square c over dx square equal to 8 plus 54,000 over x cubed. Substitute x equal to 15 and simplify. You will get d square c over dx square equal to 24, which is greater than 0. Thus, C is minimum at x equal to 15 centimeter. Substitute x equal to 15 into C. You will get C equal to 2,700 ringgit. To check your understanding on today's lesson, please do the following exercise. In the next lesson, you will learn about Rolle's theorem and mean values theorem.